Welcome to solverfy.
So we're told that we weld a C channel onto a W section to make it stronger. We're given information about the different sections that we use. So we can look these up in the table and get their areas and their centroidal, where their centroids are with respect to some geometry on this body and their area moments. And so for the C channel, we have these properties here, and we have to be a little careful about looking at, because in the book this is the y-axis for the C channel. This is the centroidal y-axis, and this is the x-axis for the C channel. So we got to be a little careful about how we use those, because we've rotated our C channel. Now we know that the centroidal, I've defined an axis down here to try to figure out where this centroid is. And we know that, the total area. And we know that we can find this, the distance from here to the centroid of the I-beam. And we can find this, the distance from here to the centroid of the C channel. The centroid of the I-beam, we can look up its height, and it's going to be at the center, assuming it's uniform. So that's 231 millimeters. And then the centroid of the C channel, we can go find this distance to this point. That's 462 millimeters. And then the distance from this point to this point is 66 millimeters. And then the distance from this point to this point, the centroid, is 16.1 millimeters. So we get 462 plus 66 minus 16.1. And if we plug all those numbers in, we get that the centroid of the total cross section is 278.0 millimeters up from here. So that's where we are. And again, it's higher than this, as we'd expect, because we've added mass above the centroid of the I-beam. Now we can look up the area moment, the centroidal area moment properties of the I-beam from the table. And we can use the parallel axis theorem to find what they are about the x-axis, this x-axis here. And so we have it about the centroid plus its area times the distance between where the new centroid is and where its centroid is, where the centroid of the whole section is and where the centroid of that part of the section is. So that would be kind of this distance here. And we plug in our numbers, and we get 585.7 times 10 to the 6th millimeters to the 4th. Now we know that the area moment of this about the y-axis here, because the centroid x is on the y-axis, the centroid of this section is on the same as the centroid of the total section, so we just get that I_y1 equals I bar y1. Now for the area moment about the centroidal x-axis for the channel. Now we need to remember that the channel's coordinate system in the book is rotated, so this is the centroid that's listed as IY bar in the book, plus its area times the difference between where the centroidal axis, where the centroid location of the total section minus the centroid location of the C channels, and square that, and we have all these values, and we plug them in, and we get 186.2 times 10 to the 6th millimeters to the 4th. Now, again, the area moment about the centroidal, overall centroidal y-axis is the area moment about the centroidal x-axis shown in the book. So we can add up basically everything. So we take these two pieces and add them up to find the total area moment about the centroidal x-axis. And we get 744.9 times 10 to the 6th. And for the centroidal y-axis, we get 91.3 times 10 to the 6th. And those make a lot of sense because there's a lot more area away from the x-axis than there is from the y-axis. So ix is going to be a lot bigger than iy. And we can see that this was our old value for before we added the C channel onto it. And once we add the C channel on, we get this new value. So we made the bending rigidity of the beam quite a bit greater because of that C channel.